Good morning. Welcome back. This is week 17. We're finishing out semester one. Start by getting logged into Clever. So, like I said, welcome back. Welcome to 2021. Happy New Year. I want for your warm up today is what are your hopes or your dreams or your goals for 2021? All right, so like I said, this is week 17. This is lesson 32. We have two new lessons this week where we're getting some new material. Next week, we're going to be kind of doing a semester one mastery project. Today, we're starting to talk about how atoms bond. So some reminders, continue to push to get makeup work in. I did a bunch of grading right before break started and didn't do anything over break. So if you have been working on makeup work and have not seen your grade change at all, be looking for that to change this week as I start to go through and grade any makeup work that you got in. Remember, the ed puzzles are required for you if you missed the live lesson. So if you were not in lesson 32 on Tuesday or Wednesday, you should be watching this right now. The previews each week are required of you. You'll have a couple of assignments this week as we finish out the semester. Remember our expectations at the beginning of, or when we come back from a break, we always spend time going over our expectations. So remember what it means, or start to think about what it means to be safe, responsible, respectful, prepared, and here. Thank you guys for showing up. I know that it's hard to get back into the swing of things. Trust me, I'm struggling, but we got to get back into it. And hopefully in the next couple weeks, we're going to be back together in person. So I spoke briefly about makeup work. Please make sure that you're doing your makeup work. A lot of people have asked me, how can I get my grade up or what can I do to pass? And for right now, this moment, doing your makeup work is an important piece of that. You can do it without any deduction to your grade. It all needs to be in by January 10th, however. This week's work and the next week's work is due that next week to finish out the semester. But any of the other work before this, please have in by January 10th. That's this upcoming Sunday. Another opportunity for you to get some extra help if you are struggling to come to our live lessons or want some one-on-one time with me or another science teacher. There is a special program that is starting this week and will be running throughout the rest of NTI whenever that ends. But it's on Wednesdays and Fridays from 1 to 2. I will share a link on our I will share a link before it on our streams, and you can join that to get some extra help, okay? So this week, week 17, like I said, we're talking about how atoms bond. So we're pulling back to think about valence electrons, electronegativity, and then how elements will bond together based on those two things. So there are 3 assignments in addition to our preview this week. Today, you're going to get one more that goes with your that goes with this lesson. And then after our lesson on Thursday and Friday, there'll be 2 more assignments. Again, you should be simultaneously working on trying to get caught up on any old makeup work that wasn't done. Remember, please make sure that you're here watching this right now before you try and do number 73 bonding ID practice. You will be way confused if you're doing it in reverse order. So today you will need to have a periodic table open. We are finishing out our periodicity unit, so having a periodic table open is very, very important. Please make sure you have that now. All right, so before I give you your warm-up, I really quickly want to review how to do a Lewis dot diagram. This is the last thing we talked about before break. So a Lewis dot diagram is just a quicker, simpler, easier way to draw and visualize an atom. It just shows the valence electrons, which are the electrons in the outside shell of an atom. And for us, especially this week with what we're talking about, that's important because those are the electrons that are involved with bonding. So we figure out how many valence and electrons an element has by looking at the column that it is in on the periodic table. These dots that go around the element symbol represent those valence electrons. You have 4 sides with pairs of electrons appearing. You have to have 1 on each side before you pair them up. So again, remembering valence electrons come from the column. It's a valence or Lewis dot diagram is a simpler way to show instead of the Bohr model, and it's just showing the electrons that are in the outside shell. You have to place them 1 on each side before they get paired up, okay? So to remind you again about how the periodic table tells you how many valence electrons something has, the alkali metals, the first column, they have 1. The alkaline earth metals, they have 2. We skip the transition metals. There's 10 here. We skip all those. So although this is labeled as column 13, all of these elements all have 3 valence electrons. These have 4, 5, 6, 7, and then our, noble gases, they have full valence shells with 8, except for a little helium up here. It only has 1 shell, so its full shell would only need 2, okay? So let's try this. How many valence electrons does krypton have based on the periodic table? And then select which is the correct Lewis dot diagram for it. So krypton has 8 valence electrons because it is in the 8th column. It is a noble gas. So you would draw it out with 2 pairs of electrons on the 4 sides. Good work. All right, let's try beryllium. Beryllium has 2 valence electrons. It's in the 2nd column. You cannot have them paired up together. You have to have 1 on each side first before they pair up. Your last example is phosphorus. Phosphorus has 5 valence electrons. It is in the 5th column. And then you draw those out by putting 1 on each side before it gets paired up. This is important for what we're going to talk about literally right next, is the fact that there are 3 unpaired electrons, 3 open electrons that are looking for a friend to try and get to that full 8 that we are looking for. So we're going to talk about chemical bonding today and in our next lesson. We aren't diving as deep into it as we usually would, but we are going to look at and use some of the trends and concepts that we talked about earlier in the semester to help us understand how elements are going to get paired up to form molecules and meet what is called the octet rule. So to understand the octet rule, what are the max number of electrons that can be in an electron shell? How many electrons max can be in an electron shell? So the correct number is 8. If we think about our Bohr models, remember our Bohr models, the max technically for the first shell is 2, but then the shells as you keep going out are 8. 8 is a special number because 8 represents a full valence shell, and elements are stable and happy when they have a full valence shell. So if we think about our noble gases, the elements that are in that right column, that far right column with 8 valence electrons, they're literally called inert noble gases because they don't need anything else. They are already stable and happy and content because they have those 8 valence electrons. Now, the rest of our periodic table, however, needs to do a little bit of work to get to a full valence shell, to get to that octet rule. So what we'll notice is that metals, elements on the left side of the periodic table with 1, 2, and 3 valence electrons will have a tendency to give away their electrons, to relieve them of those outside electrons and leave behind their inner shells, which are meeting the octet rule and are full. The nonmetals over on the right side of the periodic table only need a couple more, and they're going to be wanting to gain electrons or share them with each other to meet their octet rule. But the octet rule is important. We need to know that 8 is what we are shooting for. So if we look at our example here with krypton, how many valence electrons does krypton need to gain to meet the octet rule? Well, didn't mean to make this a trick question, but it doesn't need any. It already has 8. It is a noble gas. It has a full valence shell and is fine just the way it is. What about phosphorus? How many valence electrons does phosphorus need to get if it has 5 and is trying to meet the octet rule? So the correct answer there is it wants to get 3. We talked about those 3 open spots, okay? So it wants 3 more. Phosphorus is a nonmetal. It's going to gain those electrons. Now this one's a little tricky. How many valence electrons does beryllium need to lose? So I told you beryllium and other metals are going to lose their electrons because instead of wanting to gain a bunch to get to 8, they will just try and lose theirs to get rid of them and leave behind their full inner shell. So how many do you think beryllium would lose to meet the octet rule? Beryllium would only need to lose 2. It would lose those 2 outside ones, leaving behind its first shell on the inside that is already full. So it still would be meeting the octet rule and have lost those 2 outside electrons. So the reason that this trend and pattern and tendency happens is because of electronegativity. This is one of the characteristics of an atom that we discussed when we were doing our CER TCT assignment, but I told you you didn't really need to know it. Well, we do need to know it now. So really all electronegativity is the tendency of an atom to attract or pull electrons towards itself. In other words, it's how strong an element is for electrons. The strongest elements that for our electronegativity, the strongest elements that will pull electrons towards themselves are the nonmetals. If we look over here, those are the red that are strong, okay? The weakest ones are over here in the bottom left. And that matched our electronegativity trend. It increased as you went from left to right and as you went from bottom to top, okay? So generally, our nonmetals up here in this right corner are going to have larger electronegativities. The reason for that is that these nonmetals want to pull electrons to themselves to meet that octet rule. Okay, we notice that the noble gases are not labeled as having an electronegativity. Why is that? They aren't pulling anybody to themselves. They are already good to go. The metals will have lower electronegativities. That's because their 1 and 2 electrons, they don't want to have to pull 6, 7 electrons to themselves. Instead, they just want to give their electrons away to something that has a higher electronegativity. And that way, everybody can meet their octet rule. So again, if we think back to our original krypton, phosphorus, and beryllium, this all continues to make sense. So krypton doesn't need any more electrons because it's already got 8. It has an electronegativity of 0. It doesn't need anything else. It's happy and full and content. Phosphorus has a pretty high electronegativity because it wants to gain its 3 more, and it's a nonmetal. Beryllium is a metal. It only has 2 electrons, and its electronegativity is pretty low. That means it wants to get rid of those 2 as opposed to pulling more towards themselves. So how does all this pulling and giving and taking work? It works to then create bonds. So there are 2 types of bonds that we are going to dive into further on Thursday. We have covalent and we have ionic bonds. So ionic bonds occur between 2 elements that have a really big difference in electronegativity. So a metal and a nonmetal, this nonmetal having such a high electronegativity that it wants to pull the electrons from the metal all the way over to themselves, taking them and snatching them fully away. Covalent bonds occur between elements that have kind of similar electronegativities, where one element is not so strong that it can fully pull the electrons all towards themselves. There's 2 types of covalent bonds, and you're going to label them today, but it's not super important that we know what those are yet. We will talk about them later because it is important when we learn about different types of molecules. But in covalent bonds, the electrons are not just fully snatched. Instead, they're shared between. So to do this, we have to calculate the difference in electronegativities between 2 elements to determine, are they going to be ionic if their difference is bigger than 1.5, or are they going to be covalent if their difference is kind of close and less than 1.4. So to do an example for you all, let's take a look here at sodium and chlorine. So sodium, if we find it on the periodic table, Na is a metal. It's over on this side of the periodic table, and it has an electronegativity of 0.9. Chlorine is over on the right side of the periodic table and is a nonmetal. Its electronegativity is 3.0. So what we do once we found that information is pretty straightforward. All we're going to do is subtract. So we take the larger electronegativity and subtract the smaller electronegativity. 3.0 minus 0.9 is 2.1. If we check this chart, any electronegativity difference that is bigger than 1.5 means you have an ionic bond. Anything that's less than that will be covalent. 2.1 is bigger than 1.5. So this bond between chlorine and sodium would be ionic. All right. So let's try this now. You're going to tell me, is calcium a metal or a nonmetal and what its electronegativity is. Next, you're going to tell me sulfur, is it a metal or a nonmetal and what its electronegativity is using this chart. Great. So what we found is calcium is a metal, sulfur is a nonmetal. Their electronegativities are this: 2.6 for sulfur, calcium is 1.0. So now you need to tell me what is the difference between them. So the difference is 1.6. 2.6 minus 1.0 is 1.6. We have a metal and a nonmetal. And that electronegativity difference, 1.6, is bigger than 1.5. So what type of bond would form between calcium and sulfur? Correct answer is ionic. Let's try another example. So looking at oxygen and bromine, is oxygen a metal or a nonmetal? And what is its electronegativity? Bromine, is it a metal or a nonmetal? And what is its electronegativity? Awesome. So oxygen is a nonmetal, bromine is a nonmetal. When you have two nonmetals, their electronegativities tend to be fairly close. So let's figure out the difference. Electronegativity of oxygen was 3.5, bromine was 2.8. 3.5 minus 2.8, what is that? The difference is 0.7. Okay, so if it is 0.7, is it less than 1.5? It sure is. It is two nonmetals, so that means it would be a covalent bond. We would have a polar covalent bond specifically. 0.7 is less than 1.4, so it's over here in the covalent. If we got specific, it is between 0.3 and 1.4, so this would be a polar covalent bond. All right, so your assignment for today, let me go open that one up and show you briefly. That assignment is going to have you practice, figuring out if these are, have you practice figuring out if you're going to have electronegativity, if the electronegativity difference between two elements is large enough for it to be a ionic or a covalent bond. So looking at that here, how you'll do this is it's like our ionic and covalent. No, that's a lie. Like our ion and isotope practice, if the electronegativity different, or if your correct answer is incorrect, it will remain red. Once you get the correct answer in, it will turn green. So using the chart over at the right, we see that hydrogen has an electronegativity of 2.1. If you have anything else in there, it will turn red. Okay. But if I put 2.1 and 2.1, it will then calculate the difference. So don't mess with anything over here. It will automatically calculate the difference for you. Hydrogen, although it is on the left side of the periodic table, it is a nonmetal. So we have two nonmetals with no electronegativity difference. So looking at table 2 down here, what does that tell us about what type of bond is going to form? The electronegativity difference is 0, so that means it is going to be non-polar covalent. All you'll do is then go check that box. All right, there are 6 examples for you to try on your own. Over on this side, remember, do not stop until you get these each to turn green. Okay, then you're going to check the box over here. It'll tell you the difference in electronegativity, and then check the boxes here. Okay. All right, so heading back to this, how are we feeling after this lesson? Great. And then, there's only one new assignment for you to finish out, and I hope that it goes well. Reach out with any questions. Don't be afraid to ask if you need something, and otherwise, I will see you in your next lesson. Thanks for your effort and work today. Take care, y'all. Bye.